Hello everyone. In this lab we will be demoing EE542 Lab 8. This will consist of three use cases. In first use case we will be blinking an LED on the xDot board. On the second one we will be interfacing a thermistor to the xDot and would be showing the value on putty. And on the third we will be sampling an audio signal and making an inference on it. So as a first step, I will connect the xDot module to PC, which is a Windows operating system. So now I have connected. As you can see on the device manager, the interfaces are getting updated. So it would be shown under COM port. So as you can see, there are two COM port opened at 5 and 3. The COM port 5 is used for the normal PuTTY serial communication over a UART interface, and the COM 3 is used for the passing of AT commands to the xDot. So as a next step, we have to register the xDot on the embed side. So since I have already registered, I will just log into my user ID. So as you can see, I am already registered in here. So I have also added my hardware device into it, but I will show the steps how to do that. So you go to the hardware tab and click the boards. In the filter, set it as xDot. So in this, you have to select multi-tech xDot. Yeah, so here you have to go to the step tool, which is nothing but this is just a sample program to blink an LED with 500 millisecond as the period between off and on period. So you just have to go here and import the program, which will open the compiler as a web interface, or it can be done through CLI interface also. So just give some arbitrary name to the program. So as you can see, this is the program. So it is what it is doing is within 500 millisecond period, it's plugging the LED on and off, and it's sending the system report also to the interface. So we will just go and compile this program. After the compilation, there would be a binary image created which we can download. So the compilation is done and we have got a bin file. So I would be now flashing this image to the xDot. I just copied the image, and the xDot will be opened as an external drive under my computer. And you just have to copy this file here. So So as you can see, the copying is done and it will only load this image. So you can see that file is not being shown now. And to activate this image and run in the ARM processor, we have to reset the boot. So I have now pressed the reset button. Now I will check with on the putty what is the status output. So before that, one thing I have to say is in this session I have configured my UART to 9600 speed because at 115200 there was no characters visible at the putty session. So I have figured it out by trial and error. The optimal speed is 9600. So now you can see this is the status output. At each 10 seconds this would be print, and now I am pressing the reset button so you can see the next cycle it has restarted. So at the xDot board you can see that LED lights are getting on and off with 500 millisecond as time interval between it. So these are the serial configuration which I have done at putty. COM5 9600 data bit says 8, stop it as 1, no parity bit and no flow control. Even at the device manager for the same port you can see the same values are being configured at here also. Now we would be starting the part on thermistor. So first I will be loading the code on the compiler. So from this code you can see that PB0 which is GPIO2 port is set to as an ADC analog sensor and we are using GPIO0 to drive the voltage divider circuit and this VCC will be of 3.3 volt in xDot and in the main program the read U16 function reads the voltage level from the thermistor and each voltage level is proportional to specific temperature which we can retrieve based on this equation. So that's what this thermistor function is doing and this one is done because the value which the read U16 returns is in a short int range between this value it gets normalized. So to retrieve the actual value we have to divide the obtained value by this. So now I will be compiling this image and as you can see we are also printing the temperature to the serial console. So printf will directly print it through the UART to the putty terminal and there is a sleep of 5 seconds in between the cycle. So I am compiling the program now. So as you can see it is being started. So the wiring diagram for this will be like this. So you will have a VCC here and there would be a thermistor in this one and you will have an RS10K resistor. So we have used 10K resistor here configured and the ADC pin will be connected at this point. So we are measuring the voltage drop across the RS. And this is the wiring diagram. As you can see GPIO2 pin is configured as a ADC pin and GPIO0 is configured as VCC pin. Same information you can get from this page also, the pin diagram spec. So as you can see, GPIO2 is present as P15 port and GPIO2 is present as P15 and GPIO0 is present as P17. So the code is now compiled and you can see the main image. We are downloading it. So as a first step, you have to configure the corresponding pin as ADC or normal IO port. So here we have done that thing using PIP0, which is GPIO2, and GPIO0 as a normal VCC pin with 3.3 volt. So I am downloading this image and flashing it to xDot, same procedure as previously. So it's loading now to the xDot. So it has taken the image and I will now be activating the image by pressing the reset button. So you can see that next program got loaded now. So I am now showing it on putty, the thermistor. I am restarting the xDot. So as you can see, the temperature is being shown at each interval. So it's 24 degree, 23.68 degree, 23.5967 degree, like that. And when I hit the thermistor, the temperature is getting increased as you can see now. So this is happening because due to the voltage drop across RS is increasing. So now I have stopped heating the thermistor, so now it is gradually reducing. So the code as I discussed previously, this is the code, only main logic is in this function read, pass to thermistor, convert it to corresponding temperature thing using the formula and then convert it to degree Celsius from Kelvin and just send it over to the UART. So this is the thermistor, this is the RS resistor over which we are measuring the drop, and as you can see this is the ground pin connected to the base of RS, and this is the analog ADC pin which we are measuring drop across this resistor, and this is the 3.3 volt we have dropped, and this is thermistor which is connected in series to the RS value. So that's how the xDot is working in this scenario. So now we will be concentrating on third use case. So here we are trying to generate a square wave whose output we are feeding into the LED one. So the code I will be replacing now with this one. So the functionality of this is, as you can see, we are averaging 10 values here, and we are detecting the positive slope or negative slope in the sine waveform of the audio signal. So if it is a positive slope, we will be enabling the LED to switch on, and in parallel we will be sending the signal over GPIO3 port also as a digital wave. And similarly for the negative slope also, we are switching off the LED and making the square wave to 0. And moreover, we have one more functionality, that whenever the sine wave goes to the negative peak, that is when the voltage becomes negative, we'll be detecting it here because the x dot will detect it as 0, it will clip at the 0 voltage. So we are enabling one more port for that, our GPIO2 port. So this will also be done in this use case. So now I will compile the code. So as you can see, it is being compiled. So the compilation is done. So we'll be now flashing this image. So the image is now flashed. And the image is activated now. So as you can see, this is my trace print, which is now visible. So this is the headphone jack out from the laptop, and this is the connector. You can see the ground. Then this is the reference voltage. This is the right channel, and this is the left channel. And you can see the same voltage divider circuit as previous one, which is being used. So this is the ADC pin. This is 3.3 volt. This is the ground. So the ground from the headphone jack out is connected to the ground as same as at xDot, and we have connected the right channel wire to the midpoint of voltage divider, and we are taking the value from there. So this is the wiring diagram of the third use case. So now we will be starting our test case with sound. So I have resetted the board. As you can see, now there is nothing getting displayed. Now I will start playing the audio. So audio is now being played, and you can see the sine wave negative cycle is being detected in this. And if I stop the playback, it gets stopped. Similarly, the light at the X dot also starts blinking when I have enabled the playback, and it gets stopped when the playback is stopped. Moreover, the intensity of the light is also proportional to the signal strength. That is nothing but your volume. So as your volume gets increased, the light brightness also increases, and when it gets decreased, the light shuts off. This is with 165 Hz frequency. So the next I will try is with 350 Hz frequency sine tone. So with 350 Hz also similar observation can be made. So here when it switches off, the light is off. Here when it switches on, the light is on. But here the duty cycle is 1, so you can see correctly the effect when it gets stopped and down, and also when the amplitude gets reduced, the brightness also reduces. So this is one more area. So when it is increased, it increases, and when it's decreased, the brightness decreases. So this is one more area, and you can see the same thing in here as the playback is increased and decreased. As you can see here, GPIO01 is used as a digital output, and similarly GPIO3. This indicates a negative voltage is being clamped. This is for output in square wave based on the slope of the sine wave. So now we will be starting a frequency pulse. Let's observe the behavior. So as the frequency increases, you can see a pattern change in the light on off period.
So this is because we are taking more samples in the frequency range as it increases. So the duty period is getting changed.
So with this we have concluded the use case 3. Thanks everyone for watching.